Something that we'll use a lot are the components of a vector. And the components of a vector are just a projection of the vector on the x or y axis. You can also think of it as like a shadow, if you will. So if I have a vector A right here, then it has two components, and those components are the x and the y components. I can draw those a couple different ways. So here I can draw the x component here. Notice that it's a projection, so if I were to take a line and drop it down along down to the x-axis, it would give me the length of the x component. We'll have a lab in the lab section where you actually work with these quite a bit, graphically determining the x and y components. I can also draw the y component. So here I've drawn the y component in this direction, but you can also draw the y component here, and you get something that looks very much like what we had. So let me just draw this anew over here. So if I have a vector A, I can draw its x and y components look like this. So this would be the x component. That's going to be ax. And my y component will look like this. That's ay. And notice that this is a right triangle, that the x and y components are perpendicular to one another. And so we'll use some of our right angle trigonometry in order to determine what the values are for those. So the components of the vectors add to give the original vector. And just like we were doing before with the tail to tip, so if I follow along here and then up to there, that's ax plus ay. The sum of those is going to be the vector A. So I can just write that as ax plus ay, that is the vector ax plus the vector ay, is equal to the vector A. We can use some of our trig in order to find out these values. So for example here, I have the vector A, and since it is part of a right triangle, if I know this angle theta right here, then I can find out what is the y component. It's just a sine theta. Just to remind you, sine of the angle theta is opposite over hypotenuse, and that is equal to, in these notations, the opposite is the y component over a, and then so I developed this expression for ay. Ay is equal to a sine theta. That's only true if the angle theta is measured from the x-axis. In a similar way, I can find that ax is equal to a cosine theta, and again, that is only true if the angle theta is measured from the x-axis. If instead I'm measuring an angle from up here, then those become quite different. And in fact, if I'm using that angle phi, then ay is equal to a cosine phi, and ax is equal to a sine of phi. Usually it won't matter because usually our angle will be measured from the x-axis, but you just need to be aware that you don't blindly use cosine for the x component and sine for the y component, that you understand that it depends upon where the angle is measured from. Just like we did before with trig, we can find the angle theta using the inverse tan function. Now in some cases, you might need to rotate the coordinate system. We'll see this in chapter 4, especially when we're dealing with inclined planes. It becomes a lot easier if we can rotate the coordinate system to make a problem easier. Remember, as we talked about in the previous chapter, you're the one that sets the coordinate system. So while we might have standards on what we can do, it's really up to you to set your coordinate system. And so in that way, you're able to pick whatever coordinate system you want. So for example, in this problem where you have two vectors which are off the axes, off the x and y axes, you could rotate the coordinate system so that the x-axis would align with the vector A. So you might draw it so that your x-axis would be here, and then and then your y-axis would be there. And actually, it looks like these two vectors are perpendicular, but you could say then the angle between the y-axis and the vector b, which would be this angle, would be phi minus theta. We'll see an example of this when we get into chapter 4 when we're dealing with coordinate with inclined planes, as I said. So this should be phi minus, or excuse me, not phi minus phi, phi minus theta. All right. Now to add vectors, you add their components separately. So let's say, for example, I want to know what is the vector r, and r is equal to the vector a plus the vector b. If I want to know r, my first job, actually, let me go back up here. What I've shown, I also know that r is equal to the sum of its x and y components, rx and ry. So I want to know what is the vector r. It's going to be two vectors, a and b. See if I can draw this graphically. So let's say I have a vector a and a vector b. It's my vector a, it's my vector b. I want to know the vector r. But I can also say that the vector r is the sum of its x component, this is rx, and its y component. So I'm saying this in two different ways, that r is equal to a plus b, but then the vector r is also equal to the vector sum of its x and y components. Now first I want to find the components. So I want to find ax and ay. I'm sorry, I'm missing something here. Also need to recognize that Rx is the sum, you'll see this will work a problem, Rx is going to equal the sum of Ax plus Bx. And then Ry is going to equal the sum of Ay plus By. Let me try to show you this. Let me pick another set of vectors to show you. So let's say, for example, I have my vector A, and then I have a vector B. And I want to know the vector R. So this is R, this is A, and this is B. R, A, and B. Now, I know that R is made up of certain components. R comes up here. R has an X component, and that X component comes over here. So this is Rx. But then R also has a Y component. And it looks like this. So Rx and Ry. Now I know that the vector R is equal to the sum of its X and Y components, because of what the X and Y components are. They're projections of that vector onto the X and Y axes. But notice also that A and B also have X and Y components. So my vector A has an X component that is right here. It has a Y component that is right here. Similarly, the vector B has an X component. It goes from here to here. So that is my Bx component. And then my Y component for B looks like this. So this is my AY right here. This is my AX, X and Y components for A. And then this is my BY. This is BY. and then this is bx. Notice that ax and bx add up to give me rx. So rx equals the sum of ax plus bx, and ry in a similar way gives me the sum of ay plus by. All right. We'll do this as an example in the next screencast, so you can see what that looks like. I think that's true. Let's see. Yeah, we'll pick this up. I'll actually have a problem that we can work through, and I'll show you some examples. Actually, no, I'm sorry, let's go ahead and finish this. So first, when we have components for Rx and Ax and Ay, oh no, I'm sorry, we'll pick this up in just a bit.